essentially, when you think about structural engineering, like a suspension bridge spanning a river.
Or a skyscraper.
Yeah, exactly, a skyscraper. There's this expectation of rigid mathematical precision.
Because you look at the blueprints and everything is bolted down, it's welded.
Right, it's fixed in place. The whole system is designed to handle stress through just absolute unyielding stability.
It's very binary. I mean, concrete and steel either hold the weight or they catastrophically fail.
There is no middle ground, and there is definitely no flexibility in the foundation.
None at all.
But then you look at biological engineering. You look at how the human body solves the exact same problem of carrying massive dynamic weight.
And suddenly that rigid blueprint goes completely out the window.
Completely. We are looking at a structural landscape that is incredibly dynamic, constantly adapting, and honestly, a little precarious.
It's a balancing act.
It really is. So today we are taking a deep dive into the largest, most stressed, and arguably the most mechanically complex joint in your entire body, the knee. And we're relying on a pair of incredibly detailed anatomical sources today from KenHub.
Yeah, they feature a really comprehensive breakdown of the knee joint as a whole, alongside a dedicated focus on the patella, or the kneecap.
And I have to say, these sources are dense. I mean, they dive straight into the deep end of the biomechanics with all the anatomical terminology.
They do, but they present the knee not just as a basic hinge, but as an active, living machine.
Which is exactly our mission today. We want to decode that biological engineering.
Right, to move past all that dense medical jargon.
So we can help you understand exactly how this joint carries you through a lifetime of movement, why it breaks down in highly specific mechanical ways.
And how your kneecap actually functions as this secret built-in physics hack.
Okay, let's unpack this, because before we can understand how the knee actually moves, we have to establish the foundational blueprint, right? The raw materials.
At its core, the knee joint, technically called the articulatio genu, is the meeting place of three distinct bones.
Right, so you have the femur, which is the massive thigh bone carrying all the weight of your upper body.
And then you have the tibia, the main shin bone, which receives that weight.
And sitting right in front of them is the patella.
Yeah, the kneecap.
And reading through these KenHub sources, the patella really stands out mechanically.
Oh, absolutely. It's such a unique structure.
Because the text classifies it as a sesamoid bone, meaning, well, it's not connected to other bones via standard ligaments like in a traditional joint.
Right, it's actually floating. It's embedded directly inside the quadriceps tendon.
Which means it operates entirely as a biological pulley.
Exactly. And we really need to ask why the body evolved to wedge a floating bone inside a tendon in the first place.
Right, what's the point of it?
Well, if you look at the patellofemoral joint, that's the specific area where the back of the kneecap glides against a specialized groove in the femur.
Okay.
The patella is performing a very specific manipulation of force there. By sitting inside that tendon, it creates a larger moment arm for the quadriceps muscle.
I was actually looking into the physics of that moment arm concept.
It's fascinating, isn't it?
It really is, because if your quadriceps tendon just ran straight down over the bare knee joint and attached directly to your shin,
the angle of pull would be terrible.
Right, it would be almost entirely parallel to the tibia.
So when the muscle contracted, it would mostly just pull the shin bone straight up into the thigh bone,
creating massive compressive force, but like very little actual rotational movement.
Yeah, the leverage would just be awful. It would be like trying to open a heavy door by pushing on the very edge right next to the hinges.
Oh, that's a great way to picture it. You'd be pushing so hard and it barely swings.
Exactly.
Yeah.
So by wedging this thick triangular piece of bone underneath that tendon, the body physically lifts the line of pull away from the axis of rotation.
It acts as a fulcrum.
Yes. It changes the angle of the tendon's insertion, which multiplies the mechanical advantage.
Which means the quadriceps muscle can generate significantly greater angular force, or torque, to extend your leg.
Right. So every time you kick a soccer ball, or climb a set of stairs,
or just stand up from a chair, you are relying on this built-in pulley system to multiply the raw strength of your thigh muscles.
Without the patella lifting that tendon, the basic act of standing up against gravity would require an almost impossibly large muscle mass in your thighs.
It would just drain so much energy.
Huge amounts.
So, okay, the patella gives us this immense mechanical leverage to stand up. But that multiplied force has to go somewhere, right?
It does. And while the patellofemoral articulation handles the leverage, the actual weight bearing occurs at the tibiofemoral joint.
Which is where the massive knobby ends of the femur, the condyles, where they rest directly on top of the relatively flat surface of the tibia, which the sources call the tibial plateau.
Exactly.
But if it's driving the femur straight down into the flat plateau of the shin bone, bearing the entire weight of the human body plus the multiplied force of the quads,
a lot of pressure.
Why doesn't the femur just crush the tibia into powder? I mean, bones grinding on bones would turn to dust instantly. We need a serious dispersion of that force.
And the body solves this with specialized soft tissue, specifically the menisci.
Ah, right, the shock absorbers.
Yeah, these are the famous crescent-shaped plates of fibrocartilage sitting between the femur and the tibia.
And their primary functions are to provide congruence, right, making the round femoral condyles fit more securely onto the flat tibial plateau.
That, and to absorb the massive shock of daily movement.
The sources highlighted a structural quirk here that I thought was fascinating. They aren't symmetrical.
Oh, they're not.
The medial meniscus located on the inside of your knee is shaped like an open C.
Right.
But the lateral meniscus on the outside is almost a tightly closed circle.
And that asymmetry is a reflection of how the weight shifts during different phases of movement.
Makes sense.
But their internal composition is where the real engineering brilliance lies. The menisci are not just uniform pieces of biological rubber.
They have a highly specialized zone architecture, don't they?
Exactly. The outer one-third of the meniscus is thick, it's vascularized with a dedicated blood supply, and it's packed with circumferentially arranged collagen bundles.
Okay, so the collagen fibers run in a circle around the outer rim.
Yes.
I picture that like the metal hoops wrapped around a wooden barrel.
Oh, that's a perfect analogy.
Because when you press down on the barrel, the water pressure pushes outward, and those metal hoops resist the tension to keep the barrel from bursting.
Right, so the outer third of the meniscus is built to resist that outward squishing force when you stand. It handles the tensile stress.
Wow. And then what about the inner part?
Well, meanwhile, the inner two-thirds of the meniscus thin out toward the center.
Okay.
This section is completely avascular, meaning it has no direct blood supply.
Interesting.
And the collagen bundles here are arranged radially. They point inward toward the center of the joint like the spokes of a bicycle wheel.
Which means this intersection isn't built to resist outward stretching at all?
Not at all. It is perfectly adapted for bearing direct, downward compressive weight.
It's custom engineered right down to the cellular alignment.
It really is. But even with those highly adapted shock absorbers, we still have a fundamental architectural issue.
Right, because the femur and tibia are not locked into a deep, inherently stable socket like the hip joint.
Exactly. They're practically just resting on top of one another.
Which means they have to be strapped down. And this brings us to the internal strapping system.
The ligaments.
Yeah. The sources detail the intercapsular ligaments, which are located directly inside the joint capsule itself. Can we decode this alphabet soup a bit?
Sure. These are your cruciate ligaments, the ACL, the PCL.
And it's worth pointing out that cruciate simply means cross in Latin.
Right, which perfectly describes their anatomical layout.
It makes visualizing them so much easier. They form a tight internal X shape right in the center of the knee.
And that internal cross is the crux of the joint's front-to-back stability. Because we don't have a bony socket holding things in place, those two ligaments have highly specific opposing roles.
Okay, so let's start with the ACL.
The anterior cruciate ligament attaches to the front portion of the tibia and extends backward and diagonally to attach to the femur.
And its primary mechanical job
is to stop the tibia from sliding forward underneath the femur, or conversely, stopping the femur from rolling too far backward.
Okay, so picture this. When you're sprinting and suddenly plant your foot to stop, the momentum of your upper body wants to keep pushing your thigh bone forward right off the front of your shin.
Exactly.
The ACL is the internal leash that snaps taut and prevents your knee from hyperextending backward like a flamingo.
That is exactly what it does. And then you have the posterior cruciate ligament, the PCL.
Which crosses the exact opposite way.
Right, it starts at the back of the tibia and moves forward to the femur.
So it handles the opposite physical force.
Stopping the tibia from sliding backward, preventing hyperflexion.
What's clinically interesting here here is that the sources mention the PCL is remarkably thicker.
Oh yeah, it's almost twice as strong as the ACL and possesses a much richer blood supply.
Which explains why you constantly hear about athletes suffering devastating ACL tears. But PCL tears are incredibly rare.
Right. The PCL is the beefier, heavily reinforced brother of the two. It handles less extreme deceleration forces on a day-to-day basis.
So the two ligaments basically work in a state of constant alternating tension to keep the joint centered.
Through its entire range of motion, yes.
Okay, so we have the raw bones, the pulley system for leverage, the shock absorbers dispersing the compressive force, and the crossing leashes keeping the joint centered.
All the anatomical pieces are in place.
But reading how this machine actually moves in real life, I have to push back on a specific classification in our sources.
Oh.
Which one? Well, the text initially categorizes the knee as a hinge joint.
Right.
But a standard hinge, like on a door, just swings back and forth on a single fixed pin. The knee is wildly more complex than that. Calling it a simple hinge feels like a lie, honestly. It's much weirder than that.
That's a fair point, and the medical literature does eventually refine that definition, classifying it as a modified hinge joint.
And that distinction is crucial.
Very. Because if the knee were a true hinge, like your elbow joint, it would swing on a single stationary axis.
Yeah.
But we have to look at the geometry again.
The femoral condyles are vastly larger and longer than the tibial plateau they sit on.
Right. They cannot just swing. To utilize their full surface area, they have to undergo a combined motion of rolling and gliding.
Let's break down that rolling and gliding, because if the rounded ends of the femur only rolled backward over the flat shin bone,
Like a tire rolling freely across the table.
yeah, you'd end up with the femur driving right off the back edge of the shin within the first 90 degrees of bending.
Exactly. So to prevent rolling off the edge, the femur has to correct its own position.
So how does it do that?
Imagine a car tire spinning on a patch of ice. It's rotating rapidly, but it's not moving forward, right? It's gliding in place.
Okay, I can picture that.
When you bend your knee, the rounded femoral condyles begin by rolling backward. But as the knee bends further, the tension from the ACL engages, pulling the femur forward.
So this forces the condyles to slide or glide forward even as they continue to roll backward.
Exactly. It is a highly complex synchronous movement.
It's not a hinge at all. It's this shifting, self-correcting axis of rotation.
Right.
And understanding that complex geometry actually sets up what I thought was the most brilliant aha moment in the entire deep dive.
The screw hole mechanism.
The screw hole mechanism. It is wild.
It is one of the most elegant energy-saving adaptations in human anatomy. And it all comes down to the unequal sizes of those femoral condyles we just talked about.
Right. Our sources point out that the medial condyle on the inside of the femur is physically longer
And has a more curved articular surface than the lateral condyle on the outside.
So as you're straightening your leg, reaching those last few degrees of full extension,
The lateral side essentially runs out of track first. It halts.
but the longer medial side keeps gliding backward.
Because one side stops and the other side keeps moving. The femur is physically forced to rotate inward on the tibia.
It twists.
It twists. This internal rotation of the femur, or external rotation of the tibia, depending on whether your foot is planted or in the air, effectively screws the joint tightly together.
Bringing it into what the sources call the close packed position.
Exactly. The ligaments pull taut, the bony surfaces interlock maximally, and the joint becomes entirely rigid.
So for you listening, this specific locking mechanism is exactly why you can stand in a slow-moving line for coffee for 20 minutes.
Or stand at a concert for hours.
Right, without your thigh muscles completely collapsing from exhaustion. The knee physically locks its geometry into place, allowing your skeleton to bear your body weight passively.
It gives your quadriceps a vital break.
But of course, the trade-off of a locked, rigid joint is that you cannot simply initiate flexion to take your next step.
No, bending a locked knee requires active unlocking.
So how do we unlock it?
To walk again, a very specific obliquely angled muscle at the back of the knee called the popliteus has to engage.
So the popliteus acts as the physical key to the lock,
Basically, yeah. Because of its diagonal angle across the back of the joint, when it contracts, it pulls the femur into lateral rotation.
effectively unscrewing the lock.
Exactly. It releases the tension on the ligaments, returning the joint to an open pack position so that hamstrings can actually bend the leg.
That is just incredible. You take a step, the geometry forces the lock, you rest, the popliteus pulls, it unlocks, you take another step,
And it is happening thousands of times a day, entirely subconsciously.
which functions beautifully when all the variables are aligned. But when external forces overwhelm the system, the consequences are severe.
Because the knee relies so heavily on soft tissues rather than a deep, stable bone socket, it is highly vulnerable to catastrophic failure.
Yeah, and the clinical section of our sources outlines exactly how this failure occurs. I was reading about a specific injury they detailed, ominously titled the terrible triad.
Yes.
And what blew my mind wasn't just the sheer impact required to cause it, but the fact that the foot absolutely has to be planted for the destruction to occur.
Right.
If a player is hit while they're in the air, this specific triad doesn't happen.
The planted foot is the anchor point for the destruction. The terrible triad is a very specific combination of structural tiers.
We see this a lot in field sports, right?
Yeah, predominantly in rugby or American football, where cleats physically lock the lower leg into the turf,
So the foot is entirely immobilized by the grass. Then another player tackles them, delivering a massive lateral blow striking the outside of the knee,
which creates what's called a valgus force. The knee is violently pushed inward, forced to bend laterally.
which is an angle it has absolutely zero built-in mechanism to accommodate.
Exactly. And the physics of the load dictate the sequence of failure. The knee buckles inward. The first structure to experience the massive tensile strain is the medial collateral ligament, or the MCL.
Running along the inside of the joint.
Right. The force exceeds the tensile strength of the collagen fibers, and the MCL snaps
And because it's a triad, the damage just cascades.
rapidly. The tearing of the MCL instantly opens up the joint space on the inside, causing the joint line to physically gape open.
Oh, wow.
With the inner stabilizing strap gone, that immense shear force transfers directly to the internal crossing leash.
The anterior cruciate ligament.
Yes, the ACL is drawn incredibly taut under the abnormal rotation, and it tears.
And there's one more piece, right?
Finally, we have to remember the anatomical layout. The deep fibers of the MCL are physically woven into the outer edge of the medial meniscus,
So when the MCL rips violently away from the bone, it acts like a tow cable.
literally ripping the medial meniscus apart and pulling it right out of the joint space.
That is brutal. A single heavy blow to the outside of the knee, and you lose your primary inner stabilizing strap, your front to back crossing leash, and your heavy-duty shock absorber.
All in a fraction of a second. It is a complete structural and mechanical collapse of the entire system.
It is a devastating domino effect. It perfectly illustrates how interdependent these soft tissues are.
They don't just work in isolation, they share the load.
Right. When one component fails, the mechanical stress instantly overwhelms the remaining structures.
Exactly.
So the terrible triad is what happens when massive external force overwhelms the joint. But what about when the system's own internal tension gets out of balance?
That brings us back to the patella.
Right, the kneecap. The sources detailed the mechanics of patellar dislocation, when your kneecap is physically pulled out of its tracking groove.
And there's a fascinating mechanical detail here.
When the kneecap dislocates, it almost exclusively pops out laterally toward the outside of the leg.
Always lateral. And this comes down to a biomechanical tug of war involving the quadriceps muscles.
Okay, break that down for us.
The patella is being pulled medially toward the inside of the leg by the vastus medialis muscle.
Okay.
Simultaneously, it is being pulled laterally toward the outside by the vastus lateralis and the vastus intermedius.
So the natural alignment of the leg, the way the femur angles inward from the wide hips down to the knee, creates an inherent lateral pull.
Right.
It's two strong muscles and the skeletal geometry pulling the kneecap outward, and only one muscle pulling it inward.
It doesn't seem like a balanced, sustainable system.
No, it doesn't.
To compensate for this uneven natural outward pull, the bone itself has adapted.
Really?
The condyle on the lateral side of the femoral groove projects further forward than the medial side. It creates a higher, steeper ridge,
So it acts like a physical bony wall.
basically a built-in speed bump, to stop the kneecap from being pulled too far outward during normal extension.
Okay, so the skeletal geometry provides a physical block, but the source mentioned this dislocation frequently happens to hospital patients on prolonged bed rest.
Yes, it does.
Why would simply lying in a bed for a few weeks cause your kneecap to dislocate laterally?
It is a profound example of muscle atrophy disrupting mechanical balance.
How so?
The vastus medialis, that single muscle responsible for pulling the kneecap inward, is uniquely susceptible to rapid atrophy if it's not actively recruited through weight-bearing exercise.
Oh, wow. So if a patient is on prolonged bed rest, that medial muscle loses mass and tension much faster than the lateral muscles.
Exactly. So the internal tug of war becomes completely unbalanced.
Even without walking.
Just bending the knee in bed allows the still strong lateral muscles to overpower the weakened medial muscle.
And they can generate enough unopposed lateral force to pull the kneecap up and straight over that protective bony wall.
Dislocating the joint entirely from the inside out.
That is wild. The structural integrity of the knee isn't just about bones and ligaments. It requires constant active use.
It relies on perfectly balanced dynamic muscular tension to keep everything aligned.
Well, we have covered incredible biomechanical ground today. I mean, we started looking for a rigid blueprint, and what we found was a system defined by constant adaptation.
It's incredible.
We explored a modified hinge that has to roll and glide simultaneously just to keep from falling off its own track.
Right.
We found a flowing sesamoid bone acting as a biological pulley to multiply our physical strength.
And we examined the geometric brilliance of the screw home mechanism locking our legs so we don't collapse from fatigue.
Plus, we unpacked the precarious, tightly wound cross of ligaments holding the entire balancing act together against catastrophic failure.
It is the ultimate marvel of evolutionary engineering when you break down the physics, the geometry, and the cellular specialization of the cartilage.
The sheer complexity of what must perfectly synchronize just to take a single pain-free step is staggering.
It really is a miracle of synchronization.
But I want to leave you, the listener, with one final highly provocative thought from our sources to turn over in your mind today.
Nope.
Because we have a tendency to view human anatomy as a solved science, right?
Oh, definitely. We assume the map is complete.
Yeah, we assume that because we have high-resolution MRI machines and detailed textbooks, the blueprints of the human body are universally finalized.
That every human body generally follows the exact same standard schematic.
Exactly. For decades, standard medical textbooks have taught that the knee joint receives its vital blood supply from a vascular network called the genicular anastomosis.
Right, the genicular anastomosis.
Historically, early anatomists described this as a robust, perfectly interconnected network of about 10 specific arteries forming a beautiful, predictable ring of blood supply surrounding the joint.
It was taught as a concrete anatomical fact.
But in 2013, a study by Sabal and colleagues decided to deeply investigate this textbook standard.
And the findings of that study challenged the very foundation of how we standardize anatomy.
They examined the lower limbs of numerous cadavers to map out this perfect, predictable network in modern detail, and they found that the robust, direct textbook connections simply didn't exist in the way medical science had taught for generations.
It's crazy to think about.
The classic textbooks were essentially drawing an idealized average map. Early anatomists likely studied a small handful of specific cadavers and extrapolated those findings into a universal rule.
Right, but the 2013 study revealed that human vasculature in the knee is highly chaotic and varies wildly from person to person.
Some people have certain connecting arteries, some people lack them entirely, and the pathways take highly unique routes.
It is a profound realization. It means the standard anatomical map surgeons and students have been relying on is more of a generalized suggestion than a rigid biological rule.
The body finds a way to supply the blood, but it rarely uses the exact same pipes to do it. If something as foundational, as structurally critical as the primary blood supply to our largest, most heavily stressed joint is still being rewritten, reevaluated, and corrected in medical literature.
What else about our own internal engineering are we taking for granted?
Right, what other biological blueprints do we assume are fixed and universal when they're actually wildly, beautifully unique to each individual person?
It really forces us to reconsider the entire concept of a standard human body. We are still in the process of mapping out the true extent of human individual variation.
We really are. So the next time you push yourself up from a chair, utilizing your built-in patellar pulley system, or lock your knees into their close-packed position while waiting for the bus, take a second to appreciate the absolute, localized miracle of biological engineering happening inside your own legs.
It's not a rigid, perfectly standardized steel suspension bridge.
And the blueprints might still be a little messy and unique to you, but the fact that it gracefully holds together against the massive forces of daily life is nothing short of incredible. Thank you for joining us on this deep dive. Keep questioning the blueprints.